Okay, are we live? Alright. Hello everybody. So today is an interesting one. We're gonna be having a go at a little bit of theory, just a little bit of writing down some stuff. The issue that I recently had, well, just to give some update, I think the last time I was streaming I was trying to figure out, what was it, blackjacks? No, it wasn't blackjacks. It was what was it again? Sheesh, I don't remember what I was streaming. But I was trying. Oh my god, I don't even know what was. By the way, I have a YouTube channel, so if you guys want to watch the streams that are no longer on the Twitch, you can watch my YouTube under the same username. Correctness, right. I was working on the correctness of my algorithm, which turned out to be not really an important issue because it was correct the whole time. Yes, and past few days have been rather eventful. I used blackjacks, and then which is this another library in Python to do the sampling. And then today I realized that I could reproduce the results, but when I thin them, so thinning is simply taking every nth sample of your Markov chain, and that somehow improves the result for samplers like Mala and whatever, and exaggerates the result that it beats not sampler. So what I did was to show that, was that, I don't know if I have if I want to bother explaining this, but yeah, as we thin more and more, the effective sample size here increases. You can see to the point it stops, and this is actually where it matches the ideal perfect independent sampler. So this is Mala, this is nuts, and then this is the independent sampler. So this is on this very basic Gaussian target. I think 3 dimensions with some correlation. Well, not correlation, non-isotropic. Yeah, that's what I mean. So something like this. I just realized something strange. Did I write? Is it equivalent? Okay. Yeah, okay. Yeah, no, I'm good. But yeah, so I want to know. So I managed to show this, and I showed it to my professor, and he's alright. That makes sense, but he's not terribly convinced, and he would like to see some theory being written on it about it, and it should be not too hard. But here's the catch: I've never written these things down actually, so it's good for me to practice it. And he says it's easy, so I don't expect to spend more than maybe 12 hours on it, even though my brain is gonna crack. Because when he says it's easy, it means it's easy for him, I think. Yes, so let's get started. Okay. So just a quick recap. Actually, I did this maybe just last month or like a month and a half ago. Yeah, so okay, so we have the effective sample size is equivalent to something like 1 over the integrated autocorrelation time, and then that is measured by the sum of autocorrelation of that, from at infinite lags. Okay. Alright. Oh, it's getting big. Okay. And then you get that by taking the correlation. So this is the correlation function. Wait, where is it? Here. So yeah, this is this is your process, your random process, or in this case it's a Markov chain. Doesn't have to be, I think. And then this is the mean of the empirical mean right here. And then you simply take the autocorrelation at some lag lag tau here. So this is lag tau. Okay, so you have the lag, and then this is lag 0, which means that this is in fact so this is just the, what do you call, like the variance, like the empirical, yeah, the empirical variance, I guess. Yep. And then this, so this is like the truncated sum, or rather a truncated, yeah, like a truncated term, because it's n and it's not infinity. Oh wait, no, sorry, this is, wait, what the hell is this? Why is that hat here? Wait, let me see. This is a normalized correlation function. You can estimate. Oh right, so it's an estimate. Right. Okay, it's an estimate of autocorrelation time. Oh, what's my pen? Okay. Yeah. Oh man, suddenly I'm feeling so tired. What the heck? Okay, it's only like 4 p.m. Shoot. How do I even go about doing this? Wait. I feel like the answer is actually somewhere here. Yeah, there's this paper about thinning. So I feel like that I could actually probably look for the answer here, but I'm trying to see if I can come up with it on my own. Yes. Okay. If the lag L got to autoscalar measure satisfy, then there is always a finite cost at which thinning becomes more efficient for averages of that scalar. For averages, almost. Okay, but I don't care about the efficiency in this sense. This efficiency is like statistical efficiency, but I just care about autocorrelation function. Many resemble AR process. AR process 1. AR1 process is also computer most efficient sampling. The optimal K grows rapidly. The resulting efficiency gain okay, actually I don't really know where to start. Efficiency bounds autocorrelation with 2 AR1 processes. Okay. The state space can be completely general in the analysis below. So it is using the fact that it's an AR1 form. Oh no, this Ar1 autocorrelation is my bad. How do you... I mean, I would have to find the whole thing, right? Oh, so you can do it in I mean, like literally random walk. It's not even a Metropolis Hastings. Okay. Okay. Function of dynamic variables. Oh, this is old. On the calculations of autocorrelation functions. The coherence time constant. What the heck? Liouville equation and the group property. Oof. Already I'm gone. Okay, I don't think this is for me. Okay. I mean, yeah, if I... Well, if I do a random walk, then yeah, but I guess I can write things out for like an unadjusted yeah, like an unadjusted Markov chain where you don't have, I mean, then it's easier to write things down. Then it just add things up cumulatively. So then this is no different than an AR1, right? In some sense. Is it AR1? Can I write it down? Like analytically, I mean, looks tough. Looks impossible. Oh, what is BHMC? With a restricted Boltzmann machine. Oh, this is for physics. Well, all right. And then what do you got it? Okay. Don't really understand this, but all right. Momentum refreshment generates molecular dynamics. Okay. Metropolis test. Yes. Wait, but where's the Boltzmann machine? Oh, this is the original. Okay. Yeah. Oh shoot. Alright, so input Gaussian momentum refresh dynamics test output. Throw it to input. Go to your what's GRBM? Gaussian Bernoulli restricted Boltzmann machine. And then so you train this thing with HMC, and then you get this, so that after you input you go through this. I see. So then it's like, so you have this additional thing and you trained it with a standard HMC. What is a restricted Boltzmann machine? Restricted Boltzmann machine, is it the one that has to memorize everything? That's a Boltzmann machine, right? That has to memorize all the inputs, something like that. Like the goal is to recognize the inputs or something. Must form a bipartite graph. A pair of nodes from each of the two groups of units must have a symmetric connection between them. And there are no connection between nodes within a group. What? Let me just check. This is totally tangential, but yes, this looks, I don't know. What? Hey, I apologize if I can't talk too much today. I try to focus here. But yeah, I'm trying to reading a little bit on restricted Boltzmann machine. Not that it's relevant. It comes from this paper here. It's restricted Gaussian Bernoulli restricted Boltzmann machine. Cool. In any case, I don't need this really. Okay, maybe I can just practice writing down the let's just write for an Ar1 process, right? Wait, let me see, how do I want to do this? No, it's cool. Okay, here's what I'm gonna do. Oops. Here's what I'm gonna do. Here's what I'm gonna do. I'm gonna do this. Okay, I'm gonna try to start a Zoom with myself. Video, no audio, screen, start, broadcast. Okay, and then let's see, how do we want to do this? And then I can go to here, notability. Let's go here. Let's go here. And then can I change the scene? Oh, it works, does it? Wait. Exit full screen. Wait a second. Okay, it works. Yes. Yes. Yes, 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 yes. Then I can do, what is it? Oh, sick. Okay, cool. Now we're in business. Do I have shit? My pen is not charged. Okay, I'll give it a minute then. So annoying. My Apple Pencil is not charged, unfortunately. Let's give it a minute. Okay. Alright, in the moment, I'm just gonna read a bit more about this. Here. Couldn't figure out. Yeah, so I have to get my iPad connected, so I don't know a clean way to do this. So what I did is I started, well, I don't know how to get my iPad on my computer in the start, so the best way I could do is start a Zoom meeting with myself. Seems to work reasonably well. I'm not using a MacBook, so that I can't, like, Apple doesn't make it easy to put things onto my non-Apple stuff. Okay, so I want to practice, I guess, writing the autocorrelation for a Ar1 process. So actually what I want to do is probably here, but I think I could try to start from scratch, see if that gets us anywhere. How's my pencil charging? Okay, it's charged. Not fully, but good enough. Let's begin. Okay, so I'm gonna go here again and then share my content. Start broadcast in 3, 2, 1. Okay. Sick. Okay, now we're moving. Alright. So an Ar1 process is simply defined by something like xn equals to xn minus 1 plus epsilon, where epsilon is, well, it can be anything, I guess. Do something easy. Oh, I should just do like for a random walk, right? Yeah, so for random walk, this is maybe something like this. Yeah, and I guess I can add like this, so that essentially I'm drawing from a Gaussian. Yeah, I guess this is a good time to practice as well. Okay. Choosing maximum lag. Alright. This is gonna be fast and, or not fast, this is gonna be very dirty work. I'm just gonna write a lot of things and scribble and make mistakes. But that's how I do. Okay, so now if I wanna find the, so essentially if I start with So okay, I can write down it in a different way, right? So I can say there's x0 plus sum of I, where I equals 1 to n, where 0 is like your just like your initial state, and each I is distributed as standard normal. Let's just call this a 1D process. Okay. Great. Now let's try to find the autocorrelation of lag 1. So we know, looky here, we know that the autocorrelation time is this, and then it's this, and then essentially what we care about is this. We want this. So I'll process this, I'll process value, and then this is some lag. So let's go ahead and compute that. So let's just call this an Ar1. Technically this is random walk, a very special case. Alright. Okay. And then let's now compute autocorrelation. So what we need is here, we need this, then we need this autocorrelation of x at lag t. Let's just write it down first. Let's just assume we have actually, you know, I goes from 1 to big N, and then here we'll have I equals to 1. Well, they use N, right? Okay, they use N to big N. Well, I should use sorry, I should use N2, some big N. So this is N. Oh, no, this is minus tau. So this will be mu N. Well, sorry, mu F. Actually, I shouldn't use this, right? I should just compute it precisely, right? I can just do that, right? It's quite straightforward for the case of so I think, is that a T? I thought that was a tau. That was a tau. That's a tau. Yeah, I mean, it could have been a T, doesn't really matter, but yeah, it's a tau. Did I say T? My bad. Tau should be, I guess, written smaller as well. Yes, so I could just take this, right? So it's just the expectation of the kind of off-diagonal terms. How do I... Yeah, there we go. Let me try to wrap my head this around this a little tiny little bit. Okay, I think it's the same thing in the end. Yeah, this is a finite estimate, so I don't really need this. I don't know. I mean, eventually I do, but for the sake of this exercise, probably don't need to worry about that so much. So all I need to do is to find the autocorrelation here. I mean, yeah, so it's just this formula, just this idea really. How do you say autocorrelation? Say, what's it, K? Oh no, they use their term, right? C, I don't know. Of F at lag tau. Whoop. So if I have a chain like this, I'm taking here and then I'm taking here. So I stop, there's a gap here. Okay, maybe it's more interesting for now to just find the expectation of the process. So if I do this, right, I get that this is 0. And then this is a constant, so I'm centered around here. So I think without loss of generality, I can just call this 0. And then let's consider the variance. Well, let's not write it like this. So like this. So that's just the standard definition of variance. Okay, so a bit of basic algebra. What is it? Oops. What am I doing? Okay. I feel like I've written this down before. I don't know where. I feel like I've sigma times, why is that term 0? Well, I assumed that all your epsilon, your little increments, are drawn from a standard normal and they are centered at 0. So each of these individual terms are 0, the sum is 0, and then obviously sigma is just a multiplier. Yeah. So it's a very common idea. Yeah. Okay, so this looks right, okay, so now this is cool. So if I can break it down once again, just to write it down cleanly. This is a constant. Oh, actually no, this is from some distribution. Oh well, no, let's just call it a, should I just call it a constant? Well, if I call it 0, then it doesn't matter, right? Yeah, whatever. Because technically this can be your initial point. Wait, they are all centered around 0, so the summation is very close to 0. They are all centered around 0, so the expectation is exactly 0. It's not close to 0, it's exactly 0. So this is the expectation, right? So the mean essentially, right? The expected value. Yeah, so they're all exactly 0. Yeah. Of course, as you add more and more of them, the variances will be quite large. Will be larger, but it doesn't really matter because the center is still completely exactly 0. Exactly 0. Yep. Okay. So technically this guy, this x0, could be drawn from some distribution, in which case I would need to know the distribution, let's say call it pi. We should know the expectation and variance of pi, but in this case I guess we can call it 0 and treat it as a constant. I don't know if that's sensible. I mean it is. In any case, even if it isn't, I can just do a special case where I focus where the case that it is. So let's just, let's just make it explicit here. Let's just say that x0 is just some r, something we drawn, some constant from r, the one of the real numbers. Okay, and then here, so same story, and then I get to plus. Okay, now this I gotta be careful here. Okay, I'm gonna deal with this slightly differently. So this 2 term cancels out. This term is 0 for the same reason as above. Now here, so this is the expectation of the sum squared, which means I need to take care of the cross terms. But if you think about it, they are all uncorrelated because they are all independent, right? They are all drawn from this distribution and they're independent. So the cross terms have no well, the cross terms are uncorrelated, so the expectation is 0 as well. And then, so all you get is just the squared terms, which is the variance, and the variance is 1, right? Which means oh, sum, and there's a sum, I forgot. And then there's what, n of them? There's n of them. So it's n sigma squared. That's the variance of the process. So essentially this is describing just a Brownian, well, is it a Brownian motion or random walk? Well, it's a random walk. Yep. So it's just n sigma squared. Okay. Let me just quickly sanity check it. I could just look it up, yeah. Yeah, there we go. So n sigma squared, very good. Yep. Okay. So this is a very elementary way of getting there. Okay, so the reason I need this is because later on I'm gonna rely on this. So here, see, I'm gonna need the expectation of my process and then the variance of my process. So the correlation of my process is, what is it here? Well, what do they mean by mu here? Mu as in the As in they are all identically distributed, is that what it is? And it's mu? The process has mean mu t and sigma t at time. Okay, and then the variance are time independent. So this is not time independent. No, they are time independent. Wait, are they? No, they're not time independent because there's an n term there. So, okay, so it's not, so I cannot use this. Yeah, so the process is gonna look like it's gonna go up or whatever. Actually, that's so periodic. Doesn't really matter. Like, you don't know. It's quite random. But it has this envelope. You know, depending on start out from here. And then this envelope is square root of n on the order of square root of n. This negative. Yep. So I think actually, it's this envelope here. The same thing. Yeah. Yep. Yeah, so standard deviation increases with sigma t. I don't know if you can see this. It says sigma t. Alright. Okay, so far I guess I can understand chapter 1 and 2 of a basic stochastic process. Okay, let's get rid of this. And so what I want to do is to get the autocorrelation at a lag. Oops, what's happening? Oh. Blah 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 blah. But this is not white sands, right? Yeah, this is not white sands. Let's just call this 0 in this analysis here. So the correlation between, say, xn and then xn plus tau, well, should I say minus tau? Is that what people say? Screw it, I'm just gonna call it a and b. This is very hard. Nah, that makes so little sense because I don't get to cancel out. So plus tau. What the heck? Oh. Well. Same reason, only get the cross terms. Oh, what? Wait, something's wrong. Oh, these are, wait a second. These are all independent. So what I have here is in fact sigma square. I should call this m plus 1 and then this is m plus tau. Yeah. And then this is m plus 1, this is m plus tau, technically speaking. So none of them are correlated. Right, so I am doing something like something like 1, 2, 3, and then something like 4, 5, 6. Then no matter how I crisscross them, they are all not correlated. So this is 0. It's just this. Wait, that doesn't make sense. But where does tau come in? That makes so little sense. But we have made it clear that this, therefore this is 0. Here we go. Here we go. I gotta move faster than this shit, man. Okay, wait. Where did I write something wrong? The autocorrelation of a stochastic process. Wait, hold up, what? Whoa. Wait, isn't the autocorrelation simply the expectation of this? Wait, what did I write wrong here? I don't understand. Oh no! My notation is or rather it's not accurate here. No, this is not right. Okay, hold up. So xn. So this will be saying this is the sum of ei, I equals 1 to n. Sigma. And then this is saying that it is ej tau to n plus tau. Yes. And I'm assuming there's some overlap. So this would be n, and then this would be tau. So I'm taking. Well, I shouldn't think about that, right? Because that's a finite case. I should think about n, and then this n plus tau. So n plus. No, I'm right actually. This is just a sum. Ah, shoot! I'm right. I'm right. Why would this be the case? I don't understand. Hence, yes, but how do you get this? Note that sigma, this is okay. Sigma t to sigma e, yeah. Consequently, I mean, but how do you get here? I am so bad at this. It's not even funny. But okay. I guess if I work on this, I can only get better. So gotta do it anyway. Okay, here, sig. I found it. Oh, I forgot about this part. Shoot. The correlation is not the covariance. I usually just simulate in Python. Yeah, oh no, that's what I did exactly. I simulated it and I convinced myself of it, but as my professor correctly pointed out, that a lot of these things are much more how to say, it's good to state them quantitatively in theory so that you know that it's completely airtight and you understand the arguments and you really understand what's happening instead of just buying the empirical evidence which is still pretty convincing in my opinion. But yeah, but I was silly. I misconstrued correlation to covariance. That's where I messed up. So so this is correct, but then I gotta divide by the sigma. Well, okay, let me just rewrite everything then cleanly. Minus expectation of yes, and these are 0. And this is cool. And then like I described, so if I sum them up, I'm gonna get this here, and then is that it? So I'm gonna get there's no cross terms. All I'm gonna get is the main terms. So in the end I do get 1/8. That's not right. This is covariance. Now it makes sense. The covariance is indeed equivalent to the. So this is just a star moment covariance. And this makes sense because the rest of the terms are uncorrelated. So what you get is just a variance, and you have the later terms have no contributions here. That's fine. Oh no, because this is not the variance. Again, I am so stupid. This is standard deviation. So now I can let me just write things down a little cleaner. So this term cancels off, and then this term cancels off. Yeah, so that's what you get, right? Yeah, so that's it. So in this case, if so in this particular case, to match what this page is writing, if you have your n equals tau minus 1, that's what it's saying. Oh no, or rather your tau is equals to, whoops, the tau is equals to minus 1, then this will be finding the correlation with n and n minus 1, then it will be n and n minus 1. Oh wait, why is mine upside down? Shoot. Shoot, what did I do wrong? Wait, what? Oh, yeah. Then actually, yeah, if this is -1, then the top would be n minus. What the heck am I doing? That means this would have been n minus 1 here. Then this would have been n minus 1 here, and then I would have cancelled this, and then I would be left with n minus 1 over n. Yeah, this is correct. Yeah. Okay. Yeah. So this supposes that t is positive. Yeah. So if t is equals to 0, obviously the correlation is 1. I don't know if it's useful to state it in this way, but I guess you can say, if you want to say something like this. I don't know. So what matters really is the distance between the n and tau. Yeah, writing down the mathematics helps you understand the subtleties. Yeah. I mean, usually I guess the most reliable way, or rather the most proper way to learn these things is that you do a bit of the theory, you kind of get what's going on. The theory might be hard to give you intuition sometime, but it's important. And then once you've done that, you can do some experiments to show that the theory is correct. Yeah. I guess it's, well, for the most part, it's useful to learn from experiments if the theory is impossible. I think that's an important point. And a lot of the times theory are impossible. Like the theory is just too much. You can write, nothing can be written down. In any real type of applications, it usually gets intractable really fast. Like right now I'm doing is the most simple of the simplest of the simplest. You can't even get simpler than this. You really, honestly, you can't. This is like the most baby one. Okay. This is interesting because it seems like it still depends on n. That's a bit strange actually. Actually, that's weird, huh? Why would it depend on n? The correlation between this and this should be same as this and this, right? Yeah, something's wrong. I'm not convinced. Why does it depend on n? Oh, okay, I kind of get it. Because let's say if you have a process that goes like this, you know, if it's at the start and I say that the length is 10, actually no, that makes no difference, right? It's gonna be like here, so here it's gonna be here. So why would it depend on n? So it's the ratio of tau to n. Okay, let's do his derivation. Let's do this derivation just so we know that we're saying. So we have, oops. So what we're saying is that we have right, and this is a random walk. Yeah. So the correlation between yt and yt minus 1 is equivalent to here. So the expectation of E0, and then you have whoops, shoot, no more battery. Then you have the standard deviation, which is your variance yt minus 1 square root, and this, no, this is sorry, it's not like this, it's like this. And then this is the variance of yt minus 1, in which case you cancel, you get yt. Which is something like this. Cancel. Yeah, you get one like this. That's correct, yeah. So this is one. Oh, no, of course it depends on t. Ah, yes, of course. What I'm saying is that now it just depends on. Now let's say if you have k here, this is k, this is k, this is k. Yeah. So in the t very high, yeah, because the relative difference Okay. Does this translate to mine? So if n is very high, and this is 0, then it's close to 1. Alright. So in this case, if I transform my no, yeah, this is fine. This is fine. Can I make the same approximation? Or better math dot square root. Again, I can't really view hyperlinks. Just use NP square. Yes. No. I'm just saying. Yes, I'm trying to approximate it. But yes, of course, that would be rather convenient. Is that what I get? Trying to find the equivalence here. I can expand this like this, and then I can get this. Then I can approximate this by 1 minus 2, like this. Does this look like what I have here? It's similar. See if we can simplify this a bit further. Nah. How is it so clean? Oh, because the smaller one's on top. Yeah, I should have done the other way. It's a bit annoying. Nice. Wait, I don't understand. Like, what's the significance of 67 nanoseconds? What's that? Is that somehow significant to what I'm not sure. Wait, how do I move my time taken to compute it? Yeah, square root math dot square root. Okay. 1337 square root. Shoot, so numpy is slow. That's interesting. Yeah, okay, actually I can't change it like that. I'm gonna move myself over here. Yeah, thanks. Actually, all this is not super helpful because it's just easier that like this is helpful. Okay. So the correlation of okay, so let's try to loop this back to what we know. Okay. So the correlation between xn and xn plus tau is equal to just roughly equals to I guess one could write it in several ways. Don't know which one is most helpful really, but I'm gonna stick with this. And then if it's a one leg, meaning the correlation with the next guy, it would just be this. Okay, which is, I guess, 1 over 1 plus which, if you do this, it will be 2n plus 1, 1 over 2n plus 1, and then this will be 2n on top, right? 2n plus 1 over 2n, ching ching ching. Yeah. That means at high end the correlation is it's next to nothing. This is a bit hard to understand for me. Why why is the correlation decreasing? That makes no sense. I mean, when the correlation is, when n is high, this is saying it is practically 1. But if I have, you know, each step should be equally correlated, right? What doesn't matter what happened in the past, right? Well, okay, there's the story of relative difference, but that makes so little sense, because in my perspective, what insight did we draw from this? Well, okay, I'm expecting some different insight, but right now what this is telling me is that if you have a process, I guess that now I have a little bit of a paradox. So in this case, the process is described by this kind of manner. So you start from somewhere, I call it 0, and then you choose, you know, you get to, so this is sigma, you get to plus minus sigma, right? Each time you get to plus minus sigma. So it's random, you get plus or minus, or different degrees of sigma actually, and then yeah, you start to build. So naturally, let's just call let's say the first 10 steps. The first 10 steps, most likely you will stay within some envelope. Well, I shouldn't use 10 steps, but you can think about it, a discrete version where you can only do plus or minus. So it's either up or down, right? Right now this is the, you know, continuous version, but or rather continuous state space discrete process. But if I talk about discrete space, meaning to say it's only 2 sigma, 3 sigma, 4 sigma, you know, in the first 10 steps the maximum I can go is 10 sigma, right? If I luckily get to draw everything plus for the first 10 steps, then I get 10 sigma. So you get this envelope that is linear. But probabilistically, given what I have, if it's a normal, or if you know the variance, then you can say that it's within an envelope. And what this is saying is that this sample and this sample, let's call them 2 samples, are correlated, well, because, you know, they are next to each other, and you get the second one by moving some amount from the first one. So they are related, right? So, well, intuitively it means if I tell you the first one, probably you know where the second one is with some good confidence, right? On the other hand, if I take this sample, let's use a different color, blue, and then I give you this sample instead, you can see that there's a big distance between them. Now if I say, hey look, I give you the first one, if I cover the second one, and I ask you what is the second, what is this point going to be, you don't know, right? You can say it can be here, it can be here, it can be here. It can be a good envelope, it can be a good range, and that means it's much less correlated because there's a wider gap in between, and it's not terribly hard to understand, right? So but what I'm having a bit of trouble is that this is saying that at very far away that the two are more and more correlated, right? So you can see the correlation goes to 1. When n is high, this goes to 1. When n goes to infinity, this means to say that your chain gets more and more correlated per sample. It's a very strange idea. So if you think about it, if you take this to be very, very far away, let's say this is 1001 and then this value is 1002, and then we compare two earlier points here and here, where let's say this is 65 and this is 66. So the difference is 1 and the difference is 1, right? But relatively speaking, 1 divided by 65 is much larger than 1 divided by 1001. Wait, what was this? There's a fly. So the relative difference becomes much smaller in the limit of n, which makes sense. But in the context of Markov chain Monte Carlo, right, what we have is that we have a sampler that moves here, make moves around, things like that. And then what you're saying is that just because this is further into the process, these two samples are more correlated than these two samples? I don't see that. I would assume that they are equally correlated. Like neighbors are equally correlated, but this does not seem to suggest so. Okay, I made a very big assumption here because there's a huge assumption here actually that doesn't really stand, because you can see all these samples, they are not a Markov. Well, are they a Markov chain? They are a Markov chain, but wait, are they a Markov chain? Yeah, they are. It's a Markov chain, but this, you can see that this is distributed as 0, and so you can see that every term is distributed as a different distribution, technically speaking, right? So if you line them up, right, if you say x1, x2, x3, x4, blah 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 blah, they all have different distributions, whereas whereas in Markov chain Monte Carlo, they all come from the same distribution. Now that's a very important point. And if it's same distribution, then we get the white sands stationary, which is actually where did I get it? Here. Something. Where's the white sands? Wait, where is it again? Yes. So if I have white sands stationarity, then what I can have is actually that, if it's white sands stationarity, then that means all of them will have the same. Oh, actually, I don't even need to do AR1, AR2, right? Wait, what am I thinking? Okay, now it makes much more sense, because the initial paradox that I had was that in the MCMC picture, it doesn't make sense the autocorrelation goes up, whereas in the random walk picture, it makes sense that it goes up. So the resolution is that this is stationary, this is not. This is not stationary. I think that's how I understand it. Which means that if I repeat the derivation for this guy, I expect to get a constant expectation, a constant correlation, right? So if I take yeah, so if I take the correlation of xt minus 1, this is gonna be xt t minus 1 variance xt variant xt minus 1 square root, and then these are gonna be the same, so it's just gonna be a variance. Well, this is gonna be drawn from pi. Where pi is your target, and what you're left with is just a covariance. Yeah, and then if you notice that if this term is constant, then this is previously, that's where I get my n. That's where I get my sorry, it's here. Yeah, that's where I get my n from. Oh, but there's an n here as well. Wait, hold up. Covariance. Okay, I have some sense of what's happening. It's not the best idea though. Yeah, maybe I can't do that. Oh, the battery is low. Let's see if I can. Let me try to make some sense of this. I can still do a lot here. So if I take every second sample, that means I'm doing like 2n, and then this is gonna be divided by, I guess this is gonna be kn, and then this is gonna be divided by k, and it's gonna be but this is just So instead of taking, wait, I'm confused already. So if I take the next one, every time I take one away, I mean n is now shorter by k, and every time I take one, it would be equivalent to the c k tau. Yes, so there's a k tau here, k tau. Let's look at this a little bit. What? The variance of this is asymptotically this. Yes. Monotonicity constraint can get a current condition that ensures that thinning will help. Let R be the sum for a thinning factor k greater than 1, define Rk, and R minus k equals R minus Rk, then effective efficiency of k less than 1 is equal or equals to. So this is just moving things around, maybe. Rewrite 1 as k. Yes. 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 What does this mean? Where's my SoCal notes? Yeah, it's this paper. Wait, it's asking me to save it. Can I just show it here? Yes. Can I just read it here? Is that... How do I actually read this? No paper link available. Fantastic. Good job. Wait, why is it so hard to find? What is going on? Oh. Sci-Hub? No, I have the paper in PDF. I just want something to open here. It's so weird that it's so hard to find. Is this one? Oh, there's something wrong with Firefox. Yes. What is this? What? Oh, is this the guy? Oh, this is good too. Yeah, this is the one I'm looking for. Hey, okay, found it. Actually, I don't need most of this thing actually. I need some of it. Yes. The variance of the sample mean only on 1992. Yes, so essentially this is what we are concerning with. Yeah, so it's yeah. So it's this. Thing is, can I write this down? That's the idea, right? Can I write it down? I've read this so many times, but what is 1 over, right? It's basically 1 over. Then we estimate it as 1 plus here m, and then this is that thing, and then of course you gotta multiply by the number of chains. This is effective sample per one sample, but this is total sample of what you say, n chains and n samples. Is that what it is? Wait, hold up. Wait. Oh. Variogram. I don't think this is correct, right? Looks a bit off, but let me try to search another source. Actually, this looks like the same thing. Yeah, so M should be something like M chains and N samples. Okay, so multiple chains M. Yeah, that's right. Multiple chains. Are you allowed to open Sci-Hub in your uni? I don't know. Let's try. I don't use Sci-Hub, so I don't know. So I'm on my uni network now. Let's see if I can access it. Maybe it's not working. I don't know. It's bouncing around. Oh, okay, it's showing something. Okay, let's search for oh, it's one paper. Wait, what? Oh no, this is cool. Wait, but I don't understand. Like, what was this for? Because most papers are free, no? Oh, actually, I don't know. I don't know if that's true for different areas. You have to link the exact paper. Ah. So we need. So it's more like a search. Oops. So you how do you? Oh, DOI. Ah. Okay, let's try that. I don't know if it works. Just now I think I saw one of the. Well. This one, right? Has the DOI, is it? Does this have a DOI? I don't know. How do you get the DOI actually? But if you can get it. So if a paper is behind a paywall, you can get it. I don't know if you should though. Just paste the URL. Yeah. Okay. Well, to be fair, should I do this? I don't know if that's the best idea to do it on the stream. Yeah, maybe let's not do that for here. But yeah, my university actually, I think we do have. They do allow like access to a lot of the publishers. So a lot of the paywall stuff. You just gotta sign in with like your university login, and then they just give you the access, which means the university actually paid for it. Yes. Anyway. So to tell. So all I need is really. Those papers on archive anyway these days. Yeah, exactly. For things like computer science, math, stats, physics. I guess more of the sciencey stuff are on archive. I don't know if that can be said for the humanities subject or like businessy stuff. I know a lot of the businessy stuff, like management stuff. They are done by like big corporate company stuff. So I don't know, maybe those have a paywall. The oldest papers are on archive. Yeah, but the older papers are usually uploaded somewhere, right? Like right now, this paper I'm reading, it's super old. This is 1996. 1996, quite old. Yeah, and I've written older. I had to use Sci-Hub for a literature survey. Right, nice. Google Scholar is pretty useful too. That's how I find all my citations actually. Most of it. Oh wait, what did I just do? Shoot. Oh. Okay. Oh. So I need to calculate tau for a different. Alright, I think I'm gonna take a break and then I'm gonna get back to it. So yeah, I'll be back, but yeah, probably after dinner. I don't know, but I feel kind of just listless. Okay, so I'm gonna take a short break. Alright, thanks for tuning in. Good luck with your work.